If someone asks you the color of the sky, you immediately say it's blue. It's an obvious fact, no question. But what if they ask you to prove it? Well, before we scientifically knew the sky was definitely blue, someone actually did prove it. Proofs are nice, methodical ways to show if the claims are true. Mathematicians do the same thing. For example, if they say a number is rational, they have to show it with a proof. You probably guessed how it goes. Remember the set Q? It contains any number that can be written as a fraction, which defines rational numbers. Similarly, we can prove irrational numbers too, like the square roots of prime numbers. This won't be simple, but as you're becoming a mathematician yourself, it should not be a problem. Let's check it out. So, we need to prove that root 2 is irrational and hence can't be represented as a fraction. The approach I am going to choose for this purpose is prove by contradiction, and it is very simple. We will suppose that the statement which has to be proven is wrong, and then show that the result of this proposition is not possible. This is because the claim can either be true or false. There can be no in between. Hence, we will assume root 2 is a rational number and express it in fractional p by q, where the denominator is in 0. Otherwise, the fraction would be undefined. Also, we will assume that the fraction is in its lowest form. This means that p and q have no factors in common. Like in the case of 4 upon 7, they don't have common factors, and hence the fraction can't be reduced further. Why is this important? Let's save a few answers for the end. Armed with this knowledge, let's begin by squaring both sides to get rid of the radical and rearrange the equation for p. We get p squared equals some number times 2. Let's call it equation 1. Now, according to fundamental theorem of arithmetic, if p squared is divisible by 2, then p will also have to be divisible by 2. And if p is divisible by 2, then we can write p as 2 times some whole number, say p dash. Note that too, and substitute this into equation 1. This is what you will get. Get rid of the brackets and divide both sides by 2. Now, look at this equation from the perspective of q and tell me, doesn't it look familiar? Of course it does. This time it says q squared equals some number times 2. And again, by fundamental theorem of arithmetic, if q squared is divisible by 2, then q is also divisible by 2, which as it turns out, q is also 2 times some whole number, say q dash. Note this as well and highlight these two equations. Now, recall what we assumed in the beginning. Square root 2 is rational and its fractional representation is in the lowest form. But if we divide these two, it seems like the common factor 2 contradicts the hypothesis and its fractional representation is not in its lowest form. Hence, our assumption was wrong and square root 2 is not rational. That is, it is proved that it is irrational. Great job! I know it was not easy, but let's try something similar with root 3 for better understanding. Assuming it to be rational and in its lowest divisible form, let's square both sides and isolate p squared. It shows us that 3 is a factor of p squared. And we know that if p squared is divisible by 3, then so will be p. As before, we will substitute that here. Removing the brackets, this is what we get. Quickly divide it by 3. We are left now with the value of q. You probably guessed what comes next. And once again, as we can see, p upon q is not in its lowest form, which means that root 3 is an irrational number. Using this method, We can prove any other square roots of prime numbers like 5, 7 and so on, all as irrational. And there you have it. Great job on these proofs. Are you now going to prove that the sky is blue? That may not be necessary for the next lesson, but we know you can do it if you wanted to.